Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Is my voice clear?
Yeah, okay. Yeah.
Okay, so I think it's already 9 a.m. in Jakarta time. So we will start the agenda today. Good morning from Indonesia, Jakarta time to all participants of the regional focus group meeting of the Indonesian Philips Center of Excellence or COE. And let me introduce myself. My name is Eka, and today I will be the moderator for today's Indonesian Philips COE agenda. So for our session today, focus on the discussion on understanding meteorological drought using satellite observations. So for over the next 2 hours, we will explore how satellite-based remote sensing enhances our monitoring and response to agricultural drought across Indonesia. To guide us through this topic, we are joined today by two experts from the NKG. The first one is Dr. Siswanto, MSc PhD from the Directorate of Applied Climate Services BNKG, and also we're joined by the Mr. Gede Dedi Krisnawan, MSc, from Zainuddin Abdul Majid Meteorological Station in Lombok. Good morning, Dr. Siswanto and Mr. Dedi.
Morning.
I think we already have our two speakers. Next, our agenda today explores approximately 30 minutes presentation first, and then we will followed by a joint Q&A and discussion sessions. So before we begin, please kindly keep your microphone muted during the presentations, and during our Q&A block later, feel free to use raise hand or type your question in the chat box with format name, institutions, and also the question addressed to who and the question. So our first presentations will be delivered by Dr. Siswanto, who will discuss the utilization of satellite data in relation to agricultural sector in Java, with topic satellite-based meteorological to agricultural drought indicator to support food security in Java Island. Before I hand over the floor, allow me to share his brief profile. Dr. Siswanto currently serves at the Directorate of Applied Climate Services, the NKG, and he has extensive academic background, starting in his diploma 3 in meteorology from the Academy of Meteorology and Geophysics, and his bachelor degree of science in physics from the University of Indonesia. And then he earned a master degree in Master of Science in Climate and Environmental Physics from Universitat Bern, Switzerland. And also he completed his PhD in urban climate change at the Institute of Environmental Studies, PJ, University Amsterdam in 2023. And so for Dr. Siswanto, now the floor and screen are yours.
Thank you, Baika. Hello, good morning. Is my voice clearly heard?
Yes, it's already clear.
Okay, yeah. Good morning, all, and let me thank you for introducing my name and also my background. First of all, I would like to thank you to the committee that this occasion this morning I can share our small research done a few years ago. I think that would be also very nice to share with you all. Let me share my slide. Can you see the slide right now?
It's already shared.
Is it coming already in the
Yes.
screen?
Yes.
Okay. Yeah, as the committee appointed me to share the talk about the satellite-based meteorological to agricultural drought indicator in supporting food security in Java Island. This actually based on the two papers that released in 2023, I guess, and also the next one in 2024 something or 2025. I forgot, but we will see. So this actually very relevant with our condition nowadays, where there is a kind of a potential drought in 2026 due to the strengthening of the El Nino in the mid of this year. As we see that PMKG has already released the meteorological drought warning throughout the countries, and right now we are facing the dry condition, more drier than usual, uh, while the El Nino come to the category of the strong or really strong one, very strong one, comparable to the event of 2015, El Nino 2015. And it is predicted by the BMKG that this strong El Nino will continue until October at least, and then we will see whether it's going to be a little bit down and reducing the strength, or it is continue to still in the strong category. But from the news, or right now, we already read that many location in Indonesia, many areas, many districts has already been struggling with the water crisis, also with the forest fire event in some province, for example, in Kalimantan as well as in Sumatra. And there are already question until when this El Nino 2026 will last. Yeah. So actually, we have a very good lesson learned in 2023, where the El Nino also rose to the category of strong El Nino. It was actually more or moderate, and then in one month or 2 months, and then it's come to the very strong, the strong El Nino, not very strong one. And but the impact on the ground, for example, here there are many provinces in Indonesia suffered by this severe dry seasons. For example, in Java as well as in East Nusa Tenggara, where it was making the crisis in agricultural sector as well as the water availability, especially in the eastern part of Indonesia, for example, in Nusa Tenggara province. And the strong El Nino in 2023 significantly delayed the monsoon, elevating wildfire risk and driving atmospheric temperature to the record-breaking regional height at the moment. Yeah. And actually, what the condition in the dry condition in 2023 and also potential drought in this year more or less can be explained by the hydrological cycle equation, where we have to consider the water coming from the sky, that is the rainfall, and then the water evaporate from the water bodies in on the earth, that is the evaporation, and we have to account the water availability left on the grounds from the runoff as well as the infiltration as well as the water storage. And if we consider the all conditions is started by the water coming from the sky. So that's why here we have published one of the our effort in how we can monitor, and as well as maybe in the future we can predict through the satellite the meteorological drought that can be part of the supporting alert for the food security. So here we have a study done in, actually this one is released in 2022. So we have a publication entitled Satellite-Based Meteorological Drought Indicator to Support Food Security in Java Islands. And this actually just really using the simple index that is the so-called, I know that you all, I think you all know already, that is the standardized precipitation index. And this study actually also done as one of the national priority research. It was funded through the University of Indonesia funding uh, facilitated by the LPDP or POM in the time. So here is the talk outline that I would like to share with you. First of all, we will discuss about the concept approach to drought, and then drought indicator and indices, and then the utilization of satellite-based product for drought monitoring, and then the if we can make a kind of indication if we have a climate variability play a role, and then what look like the meteorological drought. So we will utilize the data we have from 1980 to 2020, and try to connect it with the big or the giant climate variability drivers from the Pacific Ocean, that is the ENSO, and then from the left one from the ocean, Indian Ocean, that is the Indian Ocean Dipole. And this is the definition of the drought. So according to the MKG, so the drought is defined as the deficit of rainfall in a specific area within a certain period, while the IPCC define the drought as the drier than normal condition. This means that a drought is a moisture deficit relative to the average water availability at a given location and seasons. And we also maybe can refer some other definition, but in short, the drought is characterized by its severity, its magnitudes, and then its total affected area, its temporal duration, and also its seasonal timing. So then the question is that how then we can monitor the drought, and can we also provide the early warning system that can make a prevention and give the recommendation while the expected drought is coming, and what kind of drought can be put in the early warning. So here, uh, according to the scientists, actually there are 5 drought classification. It is the meteorological drought, and then the hydrological drought, and then the agricultural drought, social economic droughts, and ecological droughts. So these 5 core perspective of drought, it has a different measure, different impact, different approach. How then we can quantify the magnitude of the severity. So if we, for example, quantifying the severity from this simple graph in the right side, so we do see that what right now already operated in BMKG, for example, the use of the HTH, Hari Tanpa Hujan, or no rain days indicator, it can be failed because when a single trivial rainfall event less than 2 millimeter, but it classified as the rainfall, it can disrupt, it can reset the counter completely, masking severe ongoing water shortages still happen on the ground. For example, also there is kind of ambiguity. If the rain in Ngawi, for example, in August 2023, it is predicted by BMKG 15% below historical normal, while informative, this single deficit figure is insufficient to determine if a formal drought state has been reached in that region. So we try to learn more about the indicator that and indices that we can use. Indicator refers to the variable, measured variables that usually the agency like PMKG or Malaysia Met Service, they measure the parameter, the hydrometeorological parameter that can be used as the indicator for the drought. For example, like for the meteorological drought, as mentioned before, can use the rainfall and air temperature measurement or data. And then for the agriculture drought, it can use soil moisture and soil temperature, while the hydrological drought can use the river discharge and groundwater reservoir levels. And other drought, it's still, I think it's still very difficult to see the parameters, but we can focus only this or very relevant and also usually coming at first condition through the impact. It's first is meteorological drought and then come to the agricultural or hydrological drought. And if we can use the indices, what kind of indices that can be derived from that indicator? So here, um, the monitoring framework where the meteorological drought and then the agricultural drought and hydrological drought can be measured and also can be calculated through the indices. For example, here there are many indices that can be used already. They're available in the literature, and researcher or met operations services, they can use this kind of indices to provide a monitoring system, yeah, for the incoming drought. And there is also actually a very good guidance, that is the Handbook of Drought Indicators and Indices. So this book is really comprehensive reference guide from the easy and moderate level of indicator and indices that can be used to give the information or to give such kind of product information related drought. And also there is kind of the utilities of the utilization of the remote sensing technology in this book that can also be followed by the operational work. And here, if we focus on the utilizing the satellite-based product for drought monitoring, there are some advantages already on the ground, that some satellites, operational satellites, already give some data, or also available retrieved data from the satellite that can be used to make indices related to the meteorological drought, hydrological drought, and agricultural drought. So here is what we do in our research. So we use the satellite precipitation products from CHIRPS, from TRMM, from Persian, and also we compare it with the ground-based available precipitation grid dataset from PMKG. That is the SAOPS dataset. And here is the methodology, and the practical one is like this. So we have data in different resolution for spatial resolution, and then we regrade it or remap it to become similar or same spatial resolution. And also we make a period window, time period windows that stack all the data set into one analysis period. So here is some method and calculation. It's very simple to calculate the standardized precipitation indices come from retrieved data set from the satellite, those the satellite data set. And here we have to check the general performance. At first, we will see whether the satellite product rainfall precipitations actually can describe precisely precipitation in the area of the study. So here we focus on Java Island. So here is the annual and seasonal mean spatial distributions coming from the SAOPS. Yeah, coming from the SAOP is the yeah, it's something there. Yeah. So on the left side is the annual and seasonal mean spatial distributions. The first panel, upper panel is the chips, and then followed by TRMM and Persian. And then the below, the most below one is the observed SAOP spatial distribution of the precipitation. And then the right side is the calculated standardized precipitation index from all the data set, CHIPS, TRMM, Persian, and then SAOPS. So here we see that more or less for the annual climatology precipitation using the new normal 2000, the 20 the last 20 period of the climatology precipitation accumulation, uh, total precipitation is more or less quite good for chips and SAOPS. It gives us insight that comparable. Also, if we look at the seasonal one, this is the wet season, December, January, February, the mid one, and then the dry season in June, July, August. So here, and then if we derive there into SPI, it's also comparable between SIPS and also observed SAOPS, while to others satellite product is more or less not really giving the good performance. And if we see here also, more or less chips give us a better performance compared to other satellite product. And here is the time series from three province in West Java, Central Java, and East Java. We took for every province some locations that actually this follow the information from the Ministry of Agriculture, where this place like Karawang and then Subang, Indramayu, Cilacap, Grobogan, Sragen, Lamongan, and Ngawi, all of them are the what to say? It's like rice paddy producer for the national level for Indonesia. So those location or those district are producer for the rice highest production in Indonesia. And if we took the precipitation and SPI from there, and then we compare with the SAOPS, and make a kind of statistical evaluations matrices, here we do see that still tips give a better correlations between observation and satellite product, and also derived SPI from the satellite products. And here is the climate variability and meteorological drought. If we here the first one is the ONI indices on ONI index, that is the ocean Nino index in Pacific, Central Pacific, and also East Pacific. And the black one is the index for the Indian Ocean dipole. So we call it as the dipole mode index. And then we classified also according to the El Nino La Nina convention, that is become weak, moderate, and strong El Nino or La Nina level. And then here is the precipitation, and here is the SPI. And in SPI, we also make a kind of classification according to the usually common use in the literature, where the SPI is classified as the normal, and then moderate, very, and extreme wet. And then the below one is moderate, very, and extreme dry. So we would like to see whether this kind of fluctuation in precipitation for all location that we already mentioned before, and also the derived SPI from there is coincide with the El Nino and IOD indices here. So here we can make a kind of spatial, not spatial, but the correlation analysis between these indices, climate variability indices, with the SPI. And here we see that from these figures, meteorological drought characteristic in the study area, that is from the 8 location in Java Island, a producer, rice producer for the Indonesia, are highly dependent on variation in the El Nino and positive phase of the IOD. And drought severity in Java Island depend heavily on simultaneous intensities on both phenomena in the Pacific and in the Indian Ocean, while the timing phase is modulated by the positive IOD. That's what we conclude in our publication. So in case of a moderate to extremely dry condition, meteorological drought over Java Islands, the drought generally occur in connection with the El Nino, coupling with the IOD, with the notable exception of the early 2010, where in 2010 the La Nina, big La Nina event is happening. So drought conditions do not emerge spontaneously with the more onset of the El Nino, unless simultaneously accompanied by or rapidly followed by the onset of a positive IOD phase, such as El Nino event in 1994 and 2005 and 2018. Isolated IOD plus event occurring on their own do not generate severe drought. For example, in 2012, uh, there was a big IOD, positive IOD, but then it's not triggering the severe drought. But if we look at the 2019, when the IOD, positive IOD strengthened significantly, so we understood that in 2019 is I think this is the highest index for the positive IOD so far historically. And it is strengthened significantly after El Nino 2018 terminated. And we do see that it impacts a lot to the Indonesian precipitation, and Karhutla, forest fire, as well as the drought events occurred in that year. And if we look at the other study comparing or relating this kind of indices, climate variability indices, with the drought and affected area, the report said that the evaluation results show that the 2015 drought had the lowest SP. So actually, we do also other analysis that is using the SPEI, the following SPI. Uh, and I will show you later. And rice agriculture land affected by drought throughout 2015 was around 246,000 hectares. While in 2019 drought, as I mentioned before, it was more affected by the Indian Ocean variability, lasted longer, starting in the mid 2018, the beginning of the El Nino, weak El Nino at the moment. I think it's up to moderate El Nino, and then replaced by the very strong IOD event in Indian Ocean. And the drought impacted around 120,000 and to 223,000 hectares of rice land in 2018 and then in 2019 respectively. And this one is the continuing the SPI. We also calculated the SPEI, that is incorporating the evapotranspiration rather than precipitation only. So I think for the drought analysis, for meteorological drought analysis, this SPEI is much more robust than the SPI. And here, if we compare the event in 1997, 2006, and 2015, and then 2019, using some indices. So we compare with the SPI, SPEI, and also the PDSI. I think you know all about this kind of indices. PDSI is I haven't mentioned before. This Palmer Drought Severity Index is similar, but if we see here, SPI clearly highlight meteorological drought onset but lack soil moisture feedback, and SPEI incorporating the potential evapotranspiration, successfully incorporate temperature variable to establish clearer evapotranspiration drought trends, and using PDSI, where we also incorporate the available water content in the soil, offer the most comprehensive soil moisture profile, successfully isolating wet microclimate and affected by broad regional drought. For example, like a local convective rainfall in West Java. So here we do see that even though in SPI is already drought there, but and it's much more severe can be assessed and in PDSI, something like that we can say. I think I come to the last part of my talk. That is how then we continue from meteorological drought into agricultural drought. We have another publication. When we look down to the Citarum watershed in West Java, and then we try to find the lag between if meteorological drought is already there, and then when it's come to the agricultural drought conditions. And here we also utilizing some other method derived from the satellite product, the so-called NDVI, and we calculate the NDDI based on the vegetation index as well as the water index. And here is the, in short. So what we found is that we can then calculate the gap between meteorological and agricultural drought. Here, if the map is indicated by the red code, meaning that between agricultural and meteorological drought is more or less happening spontaneously. But then when it's come to the more green and blue one, there is time lag between meteorological drought and agricultural drought, and then the irrigation water availability from the irrigation is playing around in this term. I think that's all what I can share. It's really happy occasion that I can share this, because right now in the ground in Indonesia, operationally, the meteorological drought is released by the BMKG. We can check in the website that BMKG provide the meteorological drought. But then for agricultural drought and hydrological drought in Indonesia is still missing. And that is our homework, how then we can provide more furthermore information to the public as well as to the sector, for example, agricultural sector, as well as the society, where right now usually after a few months meteorological droughts happening, it's followed by the agricultural drought, and then the water crisis coming from the hydrological drought. I think that's all that I can share. Thank you very much for your attention, and I hope that I can hear feedback from you. Thank you.
Yeah, Okay, thank you, Dr. Siswanto, for the highly comprehensive presentations on shifting from meteorological to agricultural drought indicators and the critical impact on the food security, especially in Java. So we now shift to our focus to the second presenter. I'm pleased to introduce our second speaker, Mr. Gede Dedi Krisnawan. Mr. Dedi currently works at Zainuddin Abdul Majid Meteorological Stations in Lombok, and his educational background includes Diploma 4 in Meteorology from the State College of Meteorological Meteorology and Geophysics. And he also holds a master degree, Master of Science in Remote Sensing Science and Technology from the Center for Space and Remote Sensing Research at National Central University. He will deliver a presentation about meteorological drivers of agricultural drought in Nusa Tenggara Islands based on satellite observations. So, Mr. Dedi, you have around 30 minutes. The floor and screen are yours.
Thank you, Miss Eka, for the time. So let me share the screen. Okay, can you see my presentation?
Yes, we can see the PPT.
Okay. Okay. Good morning, everyone. Thank you for having me in this regional focus group discussion. So this is my first time to be here. My name is Gede, and I would like to say my gratitude to all of the committee in this event, and also for all of the participants, also for Mr. Siswanto. So today, I would like to present my study about the surface dryness in Nusa Tenggara Islands. So yeah, actually the study looks specifically about how the meteorological variables trigger or drive the vegetation stress and also the agricultural drought across West and East Nusa Tenggara. So, this is the outline for our discussion today. What we will cover today, there are some sections like the background, the study area, dataset, the methodology, and also the results of the study, finally the conclusion. And let me start by explaining the scientific hypothesis behind this study. So, as you can see in this figure, so this is the chain reaction between meteorological variables that leads to the agricultural drought. So, you can see in the number one first, when there is less rainfall and also less cloud cover, it will cause the surface will lose its main source of water, because when there is lack of precipitation or reduced precipitation, sometimes it will cut the surface water availability. And also during the last rainfall event, I believe that it also highly correlated with the less cloud cover. So this fewer cloud cover will cause the more incoming solar radiation to reach the surface and rises the surface temperature in the surface. And the third, when the high surface temperature increases, it also will increases the evapotranspiration rate, and finally cause the water loss from the vegetation and to the surface. So over the time, in the long-term period, if this situation occurred, like the low rainfall condition, the high incoming solar radiation intensity, and high surface temperature, this situation will create a dry and hot environment that can diminish the vegetation condition. So this is the hypothesis behind this study. So we would like to understand about how these three meteorological factors in the study, like the precipitation, the incoming solar radiation, and the surface temperature, drive the agricultural drought and vegetation condition in Nusa Tenggara Islands. So this is our study area. You can see in the panel A, the West Nusa Tenggara and East Nusa Tenggara. the location in the southern part of Indonesia, and the elevation ranging below sea level until up to 3,600 meter. And in the panel B, we can see the vegetation type classification. So as you can see, there are four dominant vegetation types here, like savanna, the dominant vegetation cover, 24.3%, following by the broadleaf forest, the croplands, and the grassland. And for the remaining area, the white color here is the non-vegetation area or the built-up areas. So the reason behind why we would like to classify the vegetation types in this study area, because we also want to know about how the different vegetation type respond to the agricultural drought situation. Okay, next, so this is our data set in this study. So we collect the thermal infrared band from Himawari to estimate the rainfall. And then we also collect the surface rainfall observation from the rain gauge in this study area to be used to validate the Himawari estimation. And we also collect some data set product from the MODIS. So as you can see, we collect the land surface temperature data, the incoming solar radiation, and the land cover classification. We also collect the surface reflectance band 1 and band 2. This data set will be used to calculate the vegetation index in the study. And all of this data set cover the period during 2019 until 2023. And yeah, we also did some resample from MODIS to be matched with the Himawari spatial resolution. So yeah, we can get the consistent grid in this study. And yeah, next, this is the temperature vegetation dryness index, or TVDI. So this is one of index that can be used to measure the or estimate the soil moisture situation condition in the surface, or to monitor the agricultural drought. So the behind concept behind this TVDI is based on the relationship between land surface temperature and the vegetation index in the x-axis. So when we plot every pixel using this index, so we can get boundaries, for example, like the dry edge and the wet edge. The dry edge here represents the soil with the maximum evaporation and also no vegetation cover. Meanwhile, for the wet edge, this represent the enough moisture and also the full vegetation cover. So based on this index, we can monitor the dryness situation, the drought and non-drought situation in the study area. And this one is the table about the drought classes based on the TVDI. So to make it easier, if the TVDI value close to 1, it means the drought event. And if the value of the TVDI close to 0, it means the no drought event. Okay, next, this is about how we estimate the rainfall. We did some filtering, and then we use the thermal infrared, or the top cloud brightness temperature from the Himawari, and we put in this equation proposed by Prakash in 2010. And then after we calculating the with this equation, we can get the rainfall estimation at 2 kilometer resolution. And we also validated the data with the 26 rain gauge station in Nusa Tenggara Islands. And in the right side, we can see the soil adjusted vegetation index. So this is our vegetation index in this study. It's quite similar with the NDVI, if you know. So, but the differences is in the function, because in the SAVI, they include the soil factor here to reduce the soil brightness effects, because some area in Nusa Tenggara Islands, I believe that the vegetation cover is sparse, so that's why it might be influenced by the soil factor. So that's why we choose SAVI as our vegetation index to reduce the impact of the soil factor. And this one is the TVDI equation, as I mentioned in the previous part. So based on the relationship between LST and the vegetation, we can monitor the surface dryness in Nusa Tenggara Islands. Okay, so this one is the statistical analysis about like the find the relationship between one variable with another variable. So we use the partial correlation. We also use the regression method, like the simple linear regression, to find the temporal lag between its meteorological factor with the vegetation and the drought. And also we calculated in the multiple linear regression combines all of the meteorological factor in the study with the temporal lag to estimate the current situation of the drought or the vegetation condition. So that's all of about the methodology. So yeah, let's move to the results part. So this is the rainfall verification matrix. As you can see, there are three temporal scale here from daily until monthly. But we can see there are six verification metrics like the R square, the normalist, root mean square error, normalized mean bias error, critical success index, POD, and FAR. But to summarizing this verification metrics, we can see, for example, like in the R square, when we accumulated the rainfall data from daily into 8 day and monthly, we can see the R square can be improved from, for example, from 0.34 until 0.70 in the monthly time scale. And this is also occur in the critical success index and also in the POD, as you can see here. And for the FAR, we can see that the value decreased during when we aggregated the data from daily into the monthly. So overall, from this verification matrix, it confirms that the estimation from the satellite in this study more reliable at the lower temporal scale in the 8 day and in the monthly time scale. So this is also support our decision to use these two time scale, the 8 day and the monthly, for the drought analysis in the further analysis, because the drought is a cumulative phenomenon. So I think 8 day and the monthly timescale is quite suitable to be used to monitor the drought situation in the study area. Okay, so this one is the slide show us the frequency of different drought intensities during 2019 until 2023. So as you can see in this figure, they are mild intensity, moderate, severe, and extreme drought intensity. And what stands out in this result, we found that this region dominantly impacted by the mild until moderate drought situation. Maybe the percentage is ranging between 5 until 40% even is the mild until moderate drought situation. And also in the panel E, we can see the total drought frequency, the combination of this intensity, and we can see that some location in this study area experience some drought situation, maybe up to 50%, as you can see in this figure. And the eastern part of Nusa Tenggara Islands clearly more vulnerable to the drought, and this condition was concentrated in the agricultural land, in the savanna, and the grassland. Okay, so this one is the monthly drought area ratio in Nusa Tenggara Island. So during 2019 until 2023. So based on this figure, we can see that the agricultural drought in this area is a persistent issue, a recurring issue, because every month we can see always there is a drought situation in this area, even in the rainfall season or in the normal season like in 2022, we can see clearly the drought or the dryness situation in Nusa Tenggara Island. So we also calculated that the moderate intensity dominantly affect the area, maybe around 50 until 60% of the total land area was impacted by the moderate drought intensity. We also found that 2019 becomes the higher or extensive drought event in the study period, following by the 2023. And this most likely because the rainfall was significantly lower during these 2 years. And we know that in 2019 and 2023, was a year where the El Nino event was active, so that's why it suppressed or reduced the precipitation during these 2 years. Okay, next, this is the TVDI or the drought situation across vegetation types in Nusa Tenggara Island. So we divided into four major vegetation types, as you can see in this box plot: cropland, forest, grassland, and the savanna. And for the mean value and the standard deviation, you can see in this table. And yeah, from this figure, we can see that the cropland and also the grassland highly vulnerable to the drought situation because they can achieve the TVDI mean value around 0.47 until 0.46, and this is the standard deviation. So this means that these two vegetation types, like the cropland and the grassland, more vulnerable in terms of the drought stress. And in the opposite, we can see in the forest region, the TVDI value, the drought situation, more lower compared to the another vegetation types in this study. And this situation might be caused by the characteristic of the forest itself, where the forests have the deep root system, so they can store the water in the deep layer of the surface, and also they also have the wide or bold canopy system in the forest area, so they more resilient compared with the another vegetation types in this study. And next, this is the study case in one of the rice field area in, I think, in Lombok, in the central Lombok. So we plot in two different years in the drought situation in the panel A during 2019 until 2020, and in the normal year during 2021 until 2022. So in this figure, we have three metrics here, like the SAVI anomaly, the vegetation condition anomaly during the study period. And also we have the SPI3. So this is the standardized precipitation index, as mentioned by Mr. Siswanto before. So this is the accumulation during 3 months, and we find the anomaly of the precipitation during the study period. And how to read the SPI value? So yeah, if the value of the SPI below than 0, it means rainfall deficit or the drought situation. And if the value is above the 0, it means wet situation. And in the opposite, for the TVDI, if the TVDI value close to 1, it means the drought situation. And if the TVDI value close to 0, it means a no drought situation. And from the panel A, we can see, for example, like in 2019 until, yeah, in the September 2019 until November 2019, we can see the minus 2 of the SPI value here. And this is also correlated with the high TVDI value during the same months, because the value of the TVDI close to 1 here. And we get the negative anomaly of the vegetation index in the rice field area during September, October, November, and December. And when the precipitation tends to increase in the rainfall season, as you can see here, the SPI move from negative value here and move to the positive value, which means the wet situation for the meteorological drought. And the TVDI decreased from the value of 1 here, decreased to below than 0.4 here. And we can see the vegetation index here move or rise from negative value to the positive value. This is for the drought season. And this one in the panel B, we can see in the normal season during 2021 until 2022. So we can see the same pattern here. The SPI 3 index show the, I think, a moderate drought situation here between -1 until -1.5 in September and October. But we can see that the TVDI value stay low below the zero point 0.4 during the normal season here. And finally, we get the positive value of the SAVI here. So this is the differences between vegetation condition in this rice field area during the drought season and in the normal season. Okay, next, this one is the vegetation response to the meteorological factors in the study. So as you can see, there are three partial correlation here between SAVI and the precipitation, SAVI and the LST, SAVI and the SR in the incoming solar radiation. So based on this figure, we can see a positive, dominantly positive correlation between SAVI and the precipitation and between SAVI and the incoming solar radiation. So these results mean the higher precipitation and the higher incoming solar radiation, it tends to help for the vegetation growth in the study area. Meanwhile, the correlation with the LST between SF SAFI and LST here show the strong and negative correlation, which means the higher surface temperature for the study area will give some negative impact for the vegetation growth. And in the panel D, we can see the dominant meteorological factor. So this is the RGB map. We combine all of the meteorological factor, and we found that dominantly this region was influenced by the land surface temperature factor, following by the precipitation in some region. That's the response of the vegetation to the meteorological factors. So next, this is the mean value and the standard deviation from the previous figure. So we can see the strongest correlation, negative correlation between SAVI and LST here, following by the incoming solar radiation and the precipitation. Okay, so this one is the result about the temporal lag between meteorological factors to influence the vegetation condition in Nusa Tenggara Island. So we plot in three map here, the temporal lag between SAVI with the precipitation, temporal lag between SAVI and LST, and with the SR here. And panel D and the panel F here show the different temporal lag for different vegetation types. And based on this result, we found that precipitation and also the incoming solar radiation actually have a 1 until 2 month temporal lag to influence the vegetation condition in this study area. Meanwhile, the LST respond to the SAVI, it has near immediate effect or response. So we can see only zero temporal lag in this panel B, the relationship between SAVI and LST. So yeah, I think it's quite interesting that we found that the precipitation and also the incoming solar radiation, they have maybe around 1 until 2 month temporal lag, and then for the LST, it has directly impact to influence the vegetation in the study area. Okay, so the next one is the drought response to the meteorological factors. In the previous bit, we have a vegetation response, okay, to the meteorological factor, but in this slide is the drought response to the meteorological factor, and we use the TVDI as an our index here. So based on the result, we can see a negative correlation between the TVDI and the precipitation here, which means the lower precipitation during the study period will cause the higher TVDI value or the dryness situation. Meanwhile, the positive correlation can be seen in the TVDI with the LST and TVDI with the incoming solar radiation, because when the LST rises and the incoming solar radiation rise, it will correlated with the high dryness situation in Nusa Tenggara Islands. And this one is the dominant meteorological factor that influence the drought situation in this area. So as you can see here, the RGB map, the land surface temperature highly influence the drought situation for this region, because the color is looks like a green until yellow color here, and the some part may be dominantly affected by the precipitation and also the incoming solar radiation. And this one is the mean value and the standard deviation from the previous figure. So we also find that the LST has the strongest correlation with the drought situation. The value may be ranging between 0.71 until 0.78 here, following by the precipitation and incoming solar radiation. Okay, so this one is the relationship between meteorological drivers. So we also want to know how the correlation between its meteorological factor in this study. So like in the panel A, we can see the correlation between precipitation and LST. In the panel B, we can see the correlation between precipitation and incoming solar radiation. And the panel C, the correlation between LST and incoming solar radiation. And we found that in panel A and the panel B, they have a negative correlation. So the lower precipitation tends to increase the LST, and the lower precipitation tends to increase the incoming solar radiation. Maybe it due to the less cloud cover during the low precipitation event. Meanwhile, the positive correlation we can see between LST and DSR, the strong positive correlation here. So for the further analysis, because the strong correlation between the LST and DSR, in our multiple linear regression model, we only prefer to use the precipitation and LST to avoid the multicollinearity problem, because the LST itself and the incoming solar radiation highly correlated, maybe the value close to 1. So that's why in this study, we only focus by using two meteorological index, the precipitation and the LST. So this is the coefficient of determination, the multiple linear regression between TVDI and these two variables. We found the value of the coefficient of determination ranging between 0.5 until 0.8, I think, in the sum region. And in the panel B, we can see the temporal lag for each pixel in this study area. So we can see the temporal lag between 8 days, 16 days, 24 days before. And this temporal lag will be used to estimate the current drought situation. Okay, I will move to the results. So yeah, this is we try to estimate the TVDI based on the meteorological variables that we have in the previous weeks with a temporal lag. And also in the left part from panel A in the panel C, this one is the TVDI, the drought situation directly calculated from the MODIS product. This one is the reference. Meanwhile, this one in the panel D until F, this is the TVDI estimation by using the temporal lag of the precipitation and land surface temperature. And as you can see, we plot in three different dates during 8 October until 24 October here. And yeah, we can see our TVDI estimation could capture the spatial distribution of the drought from the reference here. Even in the sum region, we still face the underestimation value, as you can see here, the blue color here compared to the reference. But overall, for the R square, for these three dates, we got the value above 0.60 here across the three dates that we use in this study. And for the normalized root mean square error that we achieve is be ranging between 0.07 until 0.09. And yeah, we still found the slight underestimation. But yeah, I think it's quite interesting because we can use the temporal lag time to estimate the current drought situation. So we can use the precipitation before and also the land surface temperature data in a couple weeks ago to estimate the current drought situation. So yeah, I think uh, this is the conclusion, the key findings from this study. So yeah, from this study, we found that the drought for Nusa Tenggara Island is a frequent event because this is a recurring issue every year. These islands affected by the drought situation, and the mild until moderate drought situation dominantly affected this region, and the cropland or the agricultural land the most vulnerable for the land cover in this area. And also we found that the LST, the land surface temperature, is highly influenced the vegetation condition and also the drought situation for this region. And we found the temporal lag for the precipitation and radiation between 1 until 2 months temporal lags. Meanwhile, for the multiple linear regression model, for the drought estimation, we can see that our estimation can reproduce the pattern of the drought situation, even we still got the slight underestimation in some region in Nusa Tenggara Islands. So yeah, that's all of my presentation for today. Thank you for your attention. Maybe I will give this mic back to the moderator, to Miss Eka. Thank you.
Okay, thank you very much for Mr. Dedi for your in-depth analysis regarding the meteorological drivers for agricultural drought in Nusa Tenggara region. And so we will now begin our Q&A sessions. Participant may ask question directly by using the raise hand feature, or you can submit the question in the chat box, surely by format your name, institutions, who the speakers you want to ask, and also the question. Any participants who want to ask to Dr. Siswanto or Mr. Dedi? Okay, there's one question from Miss Destri Intan Syafitri. Could you raise your hand or open your videos or okay, maybe um I will say the questions. Since the output is in spatial, that you consider to add satellite precipitation input or from either GSMAP or iMerge products to Mr. Dedi.
Okay, thank you for the question, Miss Destri. Yeah, actually, in the beginning of my study, we would like to use the iMerge product to be used as an satellite rainfall estimation. However, as far as I know, correct me if I'm wrong, that the final product of iMerge itself maybe will be released 1 month maybe or 3 months after the observation, if I'm not mistaken, right? But so based on the suggestion of the supervisor at those time, we try to use another option, which is the satellite estimation from Himawari, because based on the Himawari satellite, we can estimate the near real-time information of the precipitation, and then we can use this data set. For example, like if we want to monitor the drought situation, today we can use the accumulation of rainfall from Himawari 8 day before or 16 before, because in this study we focus on how we can estimate the drought situation based on the temporal lag. So that's why we need a higher temporal rainfall satellite. So that's why in this study we put our focus on rainfall estimation based on geostationary satellite like the Himawari. But yeah, of course, if we try to compare with the IMERS and the precipitation, I believe the performance of IMERS, I think it should be more better, because the product already have been validated across many studies. So, but yeah, in this study, our focus is to get the near real-time precipitation data. So that's why for this study, we only consider the rainfall estimation from the Himawari. So maybe that's my answer to Miss Destri.
Okay, thank you for the explanation from Mr. Dedi. Is there anyone want to ask about the topics? Pertanyaan saya Okay, maybe that's the only questions for today's sessions. So from both exam presentations today, it is clear that the satellite data provides crucial temporal and spatial solutions, and is crucial for converting the meteorological drought and data into the actionable agricultural drought monitoring both in Java, New South Tenggara regions, or it also can apply it into the other regions. So thank you once again for to the Dr. Siswanto and Mr. Gede Disnawan for your valuable insight, and to all participants that joined today's session and for the active and engaging discussions. So due to the limited time, I would like to close this session. So I'm Eka, your moderator for these sessions. I'll now hand the floor to the TSO and see you for the next regional group discussion. Thank you for the speakers today. Good morning. Oh yeah, don't forget to participants to submit the presentation and the attendance form.
Nanti untuk mewujudkan
Okay, we can leave ya.
Yeah, thank you for the presentation, Mr. Siswanto.
Ya, makasih Mbak.
Terima kasih Pak. Terima kasih Mas Dedi.